Hello everyone, my name is Qining and I use she/her pronoun. I am a third-year chemistry graduate student here at Northwestern, jointly advised by Professor Joe Hupp from the chemistry department and Professor Justin Notestein from the chemical engineering department. In my free time, I enjoy reading, playing the violin, and I've recently picked up watercolor during quarantine and I had a lot of fun painting as well. So my research focus is very interdisciplinary, spanning chemistry, chemical engineering, and material science. I am interested in synthesizing porous materials with well-defined and controllable structures. So here is what my material looks like under the electronic microscope. And if you zoom all the way into the particle into the atomic scale, you'll see that this material has a mixture of large and small pores that can take up molecules, like a sponge. And I intend to use this material as catalysts, which are substances that can accelerate chemical reactions without being consumed. Chemical reactions occur when elements in one or more reactants recombine and generate new compounds. For this process to occur, the reactants must travel through a high-energy transition state as displayed in this energy diagram. So the chemical bonds in the reactants need to break before they are able to rearrange. And this step usually requires a lot of energy. And catalysts make this process occur much more readily by lowering the activation energy it takes. I am interested in making materials to catalyze reactions between small molecules in the gas phase. Gas phase reactions are involved in some of the most important industrial processes, such as the polymerization of ethylene to make plastics, the conversion of CO2 into fuel, as well as the generation of ammonia as fertilizers from hydrogen and nitrogen gases. In the meantime, gas molecules are generally very stable, as you can see some of the bond energy of gas molecules being listed over here. Therefore, it takes a lot of energy to break the chemical bonds in gas molecules in order to rearrange the atoms or molecular fragments to make products. Therefore, finding good catalysts that can lower the activation energy during these processes is crucial to make chemical productions more sustainable. Now let's talk about chemical equilibrium. Chemical equilibrium is a thermodynamic state commonly studied in catalytic systems. This is the state in which both reactants and products are present in reaction mixture in concentrations that have no further tendency to change with time. Macroscopically, there is no observable change in the properties of the system. So how does a reaction reach chemical equilibrium? Let's take a step back and start from the initial state of a reversible reaction. At this stage of the reaction mixture contains only reactants and no products yet, and therefore we can only observe the reaction going forward, as you can see from this diagram over here. As the product accumulates, we would start to see reverse reactions as well. The overall reaction would eventually reach a state where there is no further change in Gibbs free energy, namely delta G equals to 0. At this stage, the rate of the forward reaction equals that of the reverse reaction, and we no longer observe any change in the concentrations of reactants and products. How do I incorporate the concept of chemical equilibrium in my research? Currently, I'm trying to use my material to catalyze the hydrogenation of ethylene, and the overall chemical equation for this reaction is shown here. In order to assess the performance of my catalysts, I would measure the rate constants at equilibrium at different temperatures. And I would then extract the activation energy by plotting the logarithm of the rate constants against different temperatures. According to literature, without the presence of a catalyst, The activation energy for this reaction is 87.7 kcal per mole. However, after the addition of my catalyst, I found this process takes only 11.5 kcal per mole to activate, which is very impressive. In conclusion, climate change and energy shortage are some of the most urgent issues our planet is currently facing. And that is why chemists and chemical engineers are constantly searching for better catalysts in order to pay less environmental tolls to produce chemical goods. However, no matter how great the catalysts are or how complicated a chemical process is, our work is always guided by thermodynamic concepts such as chemical equilibrium. Lastly, I want to share with you some of the most important qualities I've developed during my research journey. Those qualities are being courageous to challenge myself, being resilient to failures, and finding allies. Doing research means using the knowledge you have learned to find out more about the unknowns. Stepping out your comfort zone to make new discoveries can feel scary but ultimately rewarding. However, to get to the rewarding part, it might take tens or even hundreds of tries to succeed in a measurement or an experiment. Especially for those of you who belong to the underrepresented groups, it can be difficult to engage in the STEM field where you rarely find people who share the same identities as you. If you ever feel like an imposter or have self-doubts, please don't forget the things that keeps you interested and motivated in STEM. I, along with many other STEM professionals, will strive to create a more inclusive and equitable space in STEM so that you, the future scientists and researchers, would always feel welcomed and belonged. Thanks for listening.